Configurations, terms, levels and states. When going from a hydrogen-like atom to a multi-electron atom, the first thing we can do to make our lives easier is something called the central field approximation. This states that the potential of each electron is approximated to depend only on the distance from the center. And for each electron we can write here V central field represents the central field potential. This potential is the same for all electrons in the atom. And I represents the distance of the electron from the center of the atom. Lastly, EI is the energy of the electron. If we find the energy for each electron, we will find that it depends on two quantum numbers, Li and Ni. By specifying these quantum numbers for each electron, we get what is called the configuration of that atom, which in spectroscopic notation is denoted like this. Two atoms with the same configuration have the same energy under the central field approximation. The central field approximation is okay, but we can do a lot better. So far we have been considering the system to have this Hamiltonian, where H central field is the Hamiltonian under the central field approximation. To make this a better model, we can add the Hamiltonian containing the electric field ignored under this approximation. This extra part of the Hamiltonian leads on to the concept of a term. If we find the change in energy due to this residual Hamiltonian, we find it depends on the two quantum numbers L and S. This is assuming LS coupling, which I won't go into here. Thus by specifying L and S we get this shift in energy and also specify the term, which is denoted by this. Thus two atoms with the same configuration and term have the same energy under the central field approximation with the inclusion of the residual field. So let us dive even further into this and come up with a better approximation. We have been dealing with this Hamiltonian, including a part under the central field approximation and a part due to the residual electric field. We now include a part due to spin-orbit interactions, which leads us on two levels. If we were to find the extra energy due to this interaction, we would find it depends on the quantum numbers, L, S and J. Thus by specifying these quantum numbers we get what is called a level, which is denoted by this in spectroscopic notation. We note that specifying a level will also specify a term, and again we have assumed we are in LS coupling. Thus two atoms with the same configuration, term and level have the same energy under the central field approximation, taking into account the residual electric field and spin-orbit interactions. We are now going to assume our atom is in a magnetic field, in which case our Hamiltonian becomes this, where H magnetic is the Hamiltonian due to the presence of the magnetic field. In other words, this is the Hamiltonian due to the Zeeman effect. As you can probably guess, this leads us on two states. The change in energy due to this part of the Hamiltonian depends on the quantum numbers, S, L, J and Mj. Thus specifying these quantum numbers gives us the state of the atom. States are not commonly included within spectroscopic notation, although you should be able to see that specifying a state also specifies a level and term. Two atoms with the same configuration, term, level and state have the same energy under the central field approximation, taking into account the residual electric field, spin-orbit interactions and the effects of a magnetic field. From what we have learned, an energy level can be specified like this, which includes the configuration, the term, and the level. Thank you for watching. Any feedback is welcome.